Hi everybody, welcome to lecture 6 of Electrical Engineering 331. In this lecture we'll discuss some more facts about singularity functions, and also we will begin to consider linear systems. So first we talk a little more about singularity functions. There are a couple of ideas from chapter 1 that we have not needed for any of our problems yet, but these ideas will be very useful in the very near future, so we will discuss them now. The first idea, I'm going to introduce it in this way. Recall that the unit step function is designated as u of t and is equal to 0 when t is less than 0 and 1 if t is greater than 0. Also recall that the impulse function, which is denoted delta of t, looks like this. Is equal to 0 when t is less than 0, is equal to 0 when t is greater than 0, but when t is equal to 0, it goes to infinity, and it goes to infinity in such a way that the integral from a to b of delta of t dt is equal to 1, as long as a is less than 0, any number less than 0, and b is any number greater than 0. So what this means is that if we integrate delta function from negative infinity to t, if t is less than infinity, if t is less than 0, we get 0, and if t is any number greater than 0, we get 1. But if you compare this right-hand side here to what we wrote right up here, you will see that that is exactly equal to u of t. So therefore, we conclude that the integral from negative infinity to t of delta of tau d tau is u of t, which is just this equation with the two sides swapped. Or equivalently, we could say that the delta function, delta of t, is the derivative of u of t. So this is idea number 1. It relates the unit step function and the impulse function, and it is quite important. So this is something that you should memorize because it's just that important. It will come up that often. So memorize this. U of t is the integral of the delta function from negative infinity to t. The delta function is the derivative of u of t. Okay, well, idea number 2 is going to be a similar kind of idea, and it involves now the integral of u of tau d tau. And we're going to do this in 2 ways. First of all, we'll do it by formula, and then we'll do it graphically. So if we use a formula, recall again, u of tau is equal to 0 if tau is less than 0, and is equal to 1 if tau is greater than 0. So if we integrate the left-hand side from negative infinity to t, then we have to integrate the right-hand side from negative infinity to t. And of course, if we integrate 0 over the region from negative infinity to 0, because that's what we have. 0 is the correct expression for that entire region, so we're going to get 0 if t is less than 0. Let's say that one more time. If t is any number less than 0, then the entire integral here is in the negative region, and therefore we should use this upper expression, and when we integrate 0, we'll just get 0. But on the other hand, if t is greater than 0, then we have a portion of the integral that will be from negative infinity to 0, but that's not going to contribute anything. And then we have another portion of the integral, which is the portion over the positive region, and that's what we have here, integral from 0 to t of 1 d tau. Here, this 1 is the 1 here in the integrand. Now, if you go ahead and integrate this, we will get tau evaluated from 0 to t, and so we end up with t. And so we say then that the integral from negative infinity to t of u of tau d tau is equal to 0 for t less than 0, and it's equal to t for t greater than 0. But of course, this is just the ramp function. So we conclude that the integral from negative infinity to t of u of tau d tau is equal to r of t. And actually, now I realize I had actually intended to do that graphically as well. Let me stop this video for just a moment, and I can make a little note about that. Okay, so now we see the graphs that one would use to talk about this same idea graphically. Here is u of tau as a function of tau above, and of course it's equal to 0 over here for tau less than 0, and it's equal to 1 for tau greater than 0. And down here below is r of t. If you come out a distance t, then you go up that same distance t, because r of t is just equal to 0 for t less than 0, but it's equal to t for t greater than 0. And notice that this area under the curve, well, if t is less than 0, the area under the curve is 0, which exactly matches r of t for t less than 0. And on the other hand, if we get to the right of 0, then the area under this curve is 1 times t, which is t, which exactly matches r of t. So this down here will give you the, this value gives you the area that is under this curve up here, regardless of, for any value of t, it will work out. So either way you wish to do this, you come up with the same conclusion, which is that r of t is the integral from negative infinity to t of u of tau d tau, which is the same as saying that u of t is dr of t dt. So this second idea is also something that's very important and that you need to memorize. So now the rest of this lecture will be spent discussing a couple of ideas about linear systems. In order to be a linear system, a system must have the scaling property and the additivity property. And so for the rest of this lecture, we're simply going to talk about those two properties and make sure that you understand them. So the scaling property goes in this way. Suppose that we have some system and the input is x of t and the output is y of t. Okay. If the system has the scaling property, then when the input is cx of t, the output will simply be cy of t. So, in other words, the scaling property means that if the input is scaled by some constant, then the output will be scaled by that same constant. If a system has that property, then if a system behaves in that way, it is said to have the scaling property. If it does not behave that way, it is said to not have the scaling property. So now let me give you an example of a system that does have the scaling property, and then we'll look at an example of a system that does not. So an example of a system that does have the scaling property is a system with this input-output equation. Now again, remember that y of t is the output of the system and x of t is the input. So I'm saying that for a system that has this relationship between the output and the input, that system does have the scaling property. So let's prove that. Let's see how we can understand that that's true. So I say here, suppose that when the input is x1 of t, the output is y1 of t. So in other words, I am choosing an arbitrary input-output pair that does work for this system. The input is x1 of t, the output is y1 of t. Now, since we know that that works, that means that that must satisfy the input-output equation for the system. So, in other words, when we plug in y1 for y and x1 for x, we get a true equation. So this equation right here that I've marked with this red asterisk is a true equation. And now we want to know if when the input is c times x1 of t, is the output c times y1 of t. That's what we want to know. If that's true, then this system does have the scaling property. But if it's not true, then the system does not have that property. Okay, and you know, the way to check is just to plug in cx1 for the input here and cy1 for the output in this input-output equation and see if we get something that's true. And so that's what we've done here is we have plugged in cy1 everywhere we have a y on the left-hand side, and we've plugged in cx1 everywhere we have x on the right-hand side. And I don't know yet if it's true or not, so I'm putting a question mark over the equal sign. Okay, so now let's work on this a little bit. When we take this derivative here, remember c is a constant, so it can come outside of the derivative, and we're just left with c dy1 dt. And likewise, c and 2 are both constants, so we could pull the c outside of the 2 and write this term like this, c times 2 y1 of t. And then we bring down the equal question mark sign, and likewise over here, 3 and c are both constants, so we could interchange the order there as well. Now, down here below, I'm going to factor out a c on the left-hand side, and I'm left with dy1 dt plus 2y1 of t inside parentheses. And then the rest of the equation I just bring down exactly as it was before. Now I want to use this equation star, which I wrote down before, to substitute for dy1 dt plus 2y1 of t. You see that according to equation star, that is 3x1 of t. So I'm going to substitute that down here. And so I then have c times 3x1 of t equals question mark c times 3x1 of t. Well, obviously that's true, and so therefore this works out, and this system does have the scaling property. Now let's look at a system that does not have the scaling property, and it has a very similar input-output equation. The only difference is I have added this 1 over here on the right-hand side, but you will see that that messes it up. And now this second system does not have the scaling property. So we'll go about this in the same way to see that that's true. Okay, so again, we suppose that when the input is x1 of t, the output is y1 of t. So you should just think of this again, just as we did before, that x1, y1 is an arbitrary input-output pair. Okay, now if that is a true input-output pair, then that means that that must satisfy the equation. So if we plug in y1 for y and x1 for x, we get a true equation, and so that's what I've done, and I've just written it down here. dy1 dt plus 2y1 is 3x1 plus 1. That's what I get when I plug in x1 for x and y1 for y. Okay, so this equation with the 2 asterisks, this equation is a true equation. And now, just as before, we ask, well, if we go to cx1 as the input, will the output be cy1? Okay, and that's the same as saying if we plug in cy1 everywhere for y in this equation and cx1 everywhere for x, will we still get a true equation just like we did here? So let's check and see. So I'm going to plug in cy1 there, and I'll plug in cy1 there, and I'll plug in cx1 there. And again, I don't know if it's going to work out or not, so I'll put equals question mark. And now I need to just turn the crank and see how it works out. Now, just like before, the c can come outside of the derivative because it's a constant. So I get c dy1 dt there. And the c and the 2 can interchange. They're both constants, so I can write them in the different order, c times 2 instead of 2 times c. Again, I'll bring down the equal sign with question mark. Flip the order of c and 3 here. Okay. And then, just as before, I will factor out the c on the left-hand side to be left with c times dy1 dt plus 2y1 of t on the left, just like this, and bring down everything on the right. And then using equation with the 2 asterisks, it tells me that dy1 dt plus 2y1 is 3x1 plus 3x1 of t plus 1. So that's what I will substitute right here. I'll plug in 3x1 of t plus 1. And then when I multiply everything on the left-hand side by c, I get 3cx1 of t plus c. And on the right-hand side, if I multiply this out, I get 3cx1 of t plus 1. And then the 3cx1 of t on both sides can be canceled out. And I get c equals question mark 1. And that's not true. This must work for any c. And we see that it only works for one value of c. So therefore, this system does not have the scaling property. Now let's look at the additivity property. The additivity property goes like this. Suppose that xi of t, the input xi of t produces the output yi of t for I equals 1 to n. So really this is in statements here. It's saying that x1 of t gives the output y1 of t, x2 of t gives the output y2 of t, x3 of t gives the output y3 of t, xn of t gives the output yn of t. So suppose we know all of that information about the system. Then, if the system has the additivity property, we can say that if we sum up all of those inputs, put them all together, and then try to and then use that as the input to the system, the output will just be the sum of all these outputs. That's what the additivity property means. So, again, what we will do now, just like we did with the scaling property, we will look at one example of a system that has the additivity property and one that does not. And in fact, it turns out we can look at the very same examples that we did with the scaling property. So again, here we go back to the original system that we looked at with the scaling property. And now the way we prove it, though, is different, of course, because we're working with a different property here. So we begin with the assumption that when the input is x1 of t, the output is y1 of t, and when the input is x2 of t, the output is y2 of t. So this is just like what we have up here, but we're just going up to n equals 2. That will be enough in this case. Okay. So again, the input x1 gives us the output y1, the input x2 gives us the output y2. And so that means the fact that those two, that x1 gives us y1 and x2 gives us y2, the fact that both of those work for this system tells us actually we have two equations here. It tells us that the x1, y1 pair satisfies our input-output equation, and also the x2, y2 pair satisfies the input-output equation. So we have equation A and equation B. Both of these are known to be true. And now to check and see if this system satisfies the additivity property, what we do is we substitute in y1 plus y2 everywhere we have y, and x1 plus x2 everywhere we have x, and see if that also gives us a truthful equation. So let's see how this goes. Again, we'll plug in y1 plus y2 for y, x1 plus x2 for x, and when we do that, we get this equation right here. And as usual, I don't know if it's true or not, so I'm writing equal with a question mark. Well, over here, the derivative of a sum is the sum of the derivatives, so I can write this, and likewise, 2 times the quantity y1 plus y2 is 2y1 plus 2y2. And over here on the right-hand side, I just 3 times x1 plus x2 is 3x1 plus 3x2. Now, over here on the left-hand side, I'm going to write these 4 terms in a different order, and I'm going to group everything with y1 together, and then group everything with y2 together. But over here on the right-hand side, I'll just leave everything as it was in the previous line. Now, I will use equations A and B. Equation A tells us that this is 3x1 of t. You see right there. And equation B tells us that this is 3x2 of t. So when I make those substitutions, I get 3x1 of t plus 3x2 of t on the left-hand side, and I have 3x1 of t plus 3x2 of t on the right-hand side. And so sure enough, those are equal, and this system does indeed have the additivity property. And now we have only one more example that we have to consider, which is right here. Again, it's identical to the second example we considered with the scaling property. We're going to again look at the system with the input-output equation dy dt plus 2y of t is equal to 3x of t plus 1. And so again, when you're checking additivity, what you do is you assume that you have 2 input-output pairs that work, x1, y1, and x2, y2. Those 2 work. So you get your 2 equations. When you plug in x1, y1 into the input-output equation, you'll get dy1 dt plus 2y1 equals 3x1 plus 1. And when you plug in x2, y2 into the input-output equation, you get this second equation, which I've labeled B. And then, just as before, we now ask the question, well, if we plug in x1 plus x2 for x and y1 plus y2 for y, do we still get a truthful equation? If we do, the system satisfies the additivity property. If we don't, it doesn't. So let's check it and see. We'll plug in y1 plus y2 everywhere we see a y, x1 plus x2 everywhere we see an x, and let's see what happens. So here's d dt of y1 plus y2, 2 times y1 plus y2, 3 times x1 plus x2 plus 1. And then just as before, the derivative of the sum is the sum of the derivatives. And then when we multiply 2 times y1 plus y2, we get 2y1 plus 2y2. On the right-hand side, 3 times x1 plus x2 becomes 3x1 plus 3x2. Bring down to 1. Then, as before, we will regroup the terms on the left-hand side, grouping together everything involving y1 in the first brackets and everything involving y2 in the second brackets. And then, as usual, use these equations A and B. So this term dy1 dt plus 2y1, according to A, that's 3x1 of t plus 1. And similarly, the term dy2 dt plus 2y2 is, according to equation B, that's 3x2 plus 1. So that's where I get this. And then on the right-hand side, I just bring down what we have. And now look at what we have. The 3x1 of t on the left and right can cancel. The 3x2 of t on the left and right can cancel. And so I have 1 plus 1 on the left. So I have 2 on the left, but I just have 1 on the right. And clearly 2 is not equal to 1. So this doesn't work out. And so this system does not have the additivity property either. So that's the end of the examples for this lecture. And once again, just to quickly review, we've reviewed the relationships between various singularity functions, and we have also reviewed two properties that must be satisfied in order for a system to be a linear system. And those two properties are the scaling property and the additivity property. A system must have those two properties to be linear, otherwise it is not a linear system. So that's it for lecture 6, and good luck.